For years, we've asked what undeniable evidence of alien life would look like. In a discovery that shocked astronomers, the James Webb Space Telescope offered an answer on an object no one ever expected. When 3I Atlas drifted into our solar system, its spectrum revealed complex organic chemistry, active metabolic cycles, and radiation-resistant biological structures, patterns that simply shouldn't exist on a cold interstellar rock. It wasn't just unusual, it was alive in a way our models can't explain. This discovery cracks open the possibility that the universe is a connected ecosystem where life can move between stars and survive the impossible. If you're ready to rethink everything we believed about biology, space, and our place in the cosmos, make sure to like and subscribe. Let's get into it. NASA has released a new set of images capturing an interstellar object that immediately drew attention within the scientific community. Astronomers have classified it as a comet, and based on its chemical makeup and trajectory, many believe it may be older than the solar system itself, formed around another star long before the Sun came into existence. The earliest indication that something unusual was present did not appear as a bright flash or dramatic plume. Instead, it emerged as a faint, uneven glow, visible only at the deepest sensitivity limits of the James Webb Space Telescope. This glow was asymmetric, meaning it was not evenly distributed around the object's core, and that alone set it apart from the behavior of typical comets. Alongside this glow, Webb detected a narrow spectral feature, often described as a filament, appearing as a thin, well-defined trace within the object's light spectrum. In simple terms, a spectrum acts like a chemical fingerprint. Different materials absorb and emit light at specific wavelengths, leaving recognizable patterns behind. This particular filament did not match any known signature associated with mineral reflection, the release of gas from warming ice, or thermal radiation from heated dust. Each of those processes has been studied for decades and appears regularly in comet observations. This signal did not fit any of them. Initially, astronomers assumed the safest explanation was an observational artifact. The object, known as 3I Atlas, was already unusual simply because of its origin. It is only the third confirmed object ever observed entering the solar system from interstellar space. Previous interstellar visitors showed odd shapes and unexpected motion, but their chemistry still fell within the range of known physical behavior. Given that history, researchers approached the data with caution. They repeated the observations, checked different instruments, compared multiple exposures, and carefully ruled out background interference and calibration errors. The signal remained. Not only did it persist, but it became clearer over time. As Webb continued observing at specific infrared wavelengths, the glow intensified and appeared across multiple channels. It showed consistency in position and structure that random noise does not display. Dust clouds tend to disperse. Debris scatters unpredictably. Instrumental artifacts shift or vanish when observation conditions change. This signal did none of those things. It stayed fixed, organized, and measurable, behaving in a way that demanded further attention. Even before the most detailed datasets were fully compiled, more researchers began to recognize that something unexpected was unfolding. Webb had recorded chemical signatures that no one anticipated finding on or around a small icy body traveling alone through interstellar space. The data revealed levels of organic complexity that exceeded what is normally produced by simple, non-living chemical reactions. Organic molecules are not rare in space, but they usually appear as isolated compounds or simple chains. Here, scientists saw patterns that suggested coordination rather than chance assembly. Within the molecular absorption bands, which are specific regions of the spectrum where molecules absorb light, researchers identified repeating structures. These patterns hinted at cyclical processes. A cycle, in this context, refers to a sequence of chemical reactions that repeat over time, often associated with how living systems manage energy. The spectral fingerprint as a whole did not resemble anything previously catalogued within the solar system. At the same time, it aligned with broad expectations of biological chemistry, where molecules are organized, reused, and regulated rather than randomly distributed. As these findings circulated through research institutions and observatories, interest spread rapidly. Teams began reanalyzing archived data, while others submitted requests for additional observation time. The discussion moved carefully, but steadily, reflecting both excitement and restraint. This growing focus followed 3I Atlas as it settled into a long, shallow orbit around the Sun, allowing repeated observation without dramatic changes in its path. For decades, scientists have debated where the first strong evidence of extraterrestrial life would likely appear. Most expectations centered on distant exoplanets, particularly those with thick atmospheres. Atmospheric studies allow scientists to search for gases that are difficult to maintain without ongoing biological activity. Very few anticipated that such signals might instead appear on a small interstellar object, quietly passing through the outer regions of the solar system, carrying chemical evidence shaped far from Earth. What has surprised researchers is not only the location of these signals, but the nature of 3I Atlas itself. Unlike comets formed within the solar system, this object carries chemical fingerprints that reflect a completely different stellar environment. These fingerprints are defined by the types of molecules present and their relative proportions, which depend on the conditions under which the object formed. Temperature, radiation, and surrounding materials all leave lasting marks. In this case, those marks point clearly away from the Sun's influence and toward an alien star system. This alone makes the object rare, but the growing evidence that it may host a microscopic ecosystem has transformed its significance. It is no longer viewed solely as a foreign rock and ice body. It is increasingly considered a potential interstellar messenger, carrying information about environments humanity cannot directly visit. The signals detected by the Webb Space Telescope are weak, but their organization makes coincidence an unlikely explanation. In the mid-infrared range, a region of light where many organic molecules leave strong signatures, Webb recorded absorption patterns consistent with complex carbon-based chains. These chains display lengths and internal structures that are difficult to explain using conventional non-biological chemistry alone. Embedded within them are molecular traces associated with amino acids, which are basic building blocks of proteins on Earth. Alongside these are stable polymer frameworks, long repeating molecular backbones capable of storing structure and function. What drew particular attention was how these structures interact with energy. They absorb and emit energy in a periodic way, meaning the process follows a regular rhythm rather than a random fluctuation. This behavior closely mirrors how known living systems transfer energy to maintain internal balance. The timing of these energy exchanges is consistent across observations, suggesting an underlying regulatory process rather than isolated reactions. These patterns do not appear alone. They form layered, nested arrangements where smaller structures sit within larger ones, following shared organizational rules. On Earth, bacteria form colonies in porous environments, such as within rock or ice, where tiny cavities allow for protection and resource exchange. The structures seen around 3I Atlas follow similar principles. This does not imply identical life, but it suggests familiar modes of organization that biology often uses when conditions are harsh and space is limited. Even more compelling than the complexity is the variability. Webb has observed changes in the concentration of these molecules over time. These changes align with shifts in the object's environment as it moves closer to the Sun, receiving more energy and experiencing subtle warming. In non-living chemistry, such changes usually follow predictable paths toward equilibrium. Here, the variations appear responsive, adjusting rather than simply fading or stabilizing. As 3I Atlas travels deeper into the inner solar system, these time-dependent signals have become central to a hypothesis now being explored seriously. The idea is that the object may contain not just organic material, but life itself. Not visible organisms, not complex multicellular structures, but microscopic life. Life that operates at scales far below direct observation, yet still meets basic criteria such as organization, energy use, and responsiveness to environmental change. Some scientists suggest the presence of extremely hardy microbes adapted to survive intense cold, radiation, and long periods of isolation during interstellar travel. Others, speaking more cautiously, propose that the signals could represent remnants of a much older biological environment, perhaps originating from a planet or system that no longer exists. In this view, what remains is not an active ecosystem, but a lingering biochemical echo preserved within ice and rock. Regardless of which explanation proves correct, 3I Atlas is forcing a reassessment of long-standing assumptions about where life can exist. If life can persist on a small body without an atmosphere, without stable temperatures, and without a planetary magnetic shield, then the concept of habitability must expand. The implications reach beyond traditional astrobiology. They suggest a universe where life is not anchored to planets alone. In such a universe, microscopic carriers of life could drift silently across immense distances, traveling between stars embedded in ice and dust. Life would no longer be confined to the place where it originated. It could disperse, survive transit, and potentially influence new environments far from its source. What unsettles many scientists is not only the possibility of life migrating through space, but the deeper question that follows. Are we seeing the first evidence of a vast galactic biological web, where primitive life forms are transported across the cosmos, either accidentally or intentionally? As 3I Atlas continued its path deeper into the solar system, the pace and intensity of data collection increased sharply. What had once been a secondary observational target quickly became a top priority. The James Webb Space Telescope adjusted its observing schedule across nearly every available time window. In some cases, Planned observations of distant galaxies were delayed so that Webb could focus on collecting individual photons from an interstellar object passing comparatively close to the Sun. This level of prioritization is rare and reflects how unusual the early results already appeared. A closer object allows scientists not only to see it more clearly, but also to track how its signals change over time, which is often more revealing than a single snapshot. What began as a small research effort focused on a handful of spectral irregularities expanded rapidly. The project grew into a broad international collaboration involving specialists from many fields. Microbiologists were brought in to evaluate whether the chemical patterns were consistent with known life processes. Planetary chemists worked to determine whether any non-living reactions could plausibly produce the observed ratios of compounds. Astrophysicists refined models of radiation exposure and thermal behavior. Evolutionary scientists examined whether the inferred behaviors could make sense over long timescales. Researchers who study the origin of life joined the effort to assess whether these signatures fit within existing theories of how life first emerges from chemistry. The atmosphere within the scientific community was tense but controlled. Every new data point was examined with unusual care. Independent teams repeated analyses using different assumptions and methods. Spectral libraries were rechecked. Statistical thresholds were recalculated. The goal was not to confirm a dramatic conclusion, but to eliminate every reasonable alternative explanation. The closer 3I Atlas moved, the more complete the data became, and the harder it was to dismiss what was being observed. Curiosity gradually mixed with a sense of unease, not because of fear, but because the implications challenged ideas that had been considered stable for generations. Some researchers began to voice a cautious thought. If 3I Atlas truly carried life, it was unlikely to be a random accident. That raised difficult questions. One possibility was that the object represented a remnant of an ancient biological transport system, perhaps once used by an unknown civilization to move life across vast distances. Another possibility was less intentional, but no less unsettling, that the galaxy itself supports a natural mechanism for spreading life, a large-scale process that maintains biological diversity across star systems. These ideas remained speculative, but they could no longer be ignored outright. The central challenge remained clear. Scientists needed to distinguish between signs of life and strange but entirely inanimate chemical reactions. This task is difficult even within the solar system, where conditions are relatively well understood. In the case of an object formed around another star, the difficulty increases significantly. Chemical environments beyond the solar system may differ in ways that exceed familiar norms. Reactions that seem unlikely under local conditions might be more common elsewhere. For this reason, skepticism remained strong, and rightly so. Over time, however, cumulative modeling began to erode the remaining doubts. Rather than relying on a single observation, scientists combined multiple lines of evidence into integrated models. Each new dataset placed tighter limits on what non-living chemistry could explain. The ratios of organic compounds detected on 3I Atlas were consistently unbalanced in ways that purely abiotic processes struggle to produce. Simple chemistry tends to move toward equilibrium. Here, certain compounds appeared repeatedly favored, while others remained suppressed, suggesting selective processes at work. Periodic fluctuations in molecular concentrations added to the puzzle. These changes followed recognizable patterns rather than random variation. In simple terms, the system appeared to adjust itself. When concentrations rose too high, they declined. When they dropped, they increased again. This kind of behavior points toward a dynamic feedback mechanism, where internal processes regulate change over time. Feedback is a basic feature of living systems, allowing them to remain active under shifting conditions. Some spectral lines also suggested the presence of radiation-absorbing compounds, similar in function to biological pigments. Pigments are molecules that interact with light, either to harvest energy or to protect against damage. In the harsh environment of interstellar space, where radiation is intense and temperatures are extremely low, such compounds would offer a clear advantage. They could help a system survive sudden changes as it moves through different regions of space, including transitions into stronger stellar radiation. As the data grew clearer, skepticism began to shift toward cautious confidence. The turning point came when Webb recorded an unusual, nearly explosive burst of infrared fluorescence. At the precise moment, 3I Atlas experienced increased solar radiation. The response was not a simple rise and fall expected from heating alone. Instead, the intensity increased rapidly, then declined in a controlled pattern. This sequence closely resembled how known biological systems respond to light exposure, activating processes and then regulating them to avoid damage. From this behavior, scientists inferred that whatever was producing the signal was not merely absorbing energy passively. It appeared capable of using, or at least regulating, the energy it received. This suggested a form of simple metabolic activation, not complex metabolism as seen in larger organisms, but a basic system capable of responding to energy availability. That single observation was enough to force a reconsideration of many assumptions about the limits of life. If confirmed, the life forms associated with 3I Atlas would not be passive passengers frozen in ancient ice and locked in permanent inactivity. They would be active survival entities, capable of brief awakenings, energy regulation, and long periods of minimal activity. Such a strategy would allow survival through millions of years of isolation, punctuated by rare moments when energy becomes available. This form of existence is unfamiliar, but not incompatible with the principles of biology. In this scenario, 3I Atlas would be more than a carrier of life. It would serve as direct evidence that the universe may function as a vast ecosystem. In such an ecosystem, life does not wait for ideal conditions to appear. Instead, it persists under constraints, adapting to environments that were previously dismissed as uninhabitable. The rules governing survival would be broader than those derived solely from Earth-based examples. With each new observation, a deeper question emerged. Where did this life originate? The trajectory of 3I Atlas points back toward a region of the galaxy known for active star formation, dense nebulae, and chaotic stellar nurseries. These regions contain large amounts of gas and dust, frequent interactions between young stars, and dynamic gravitational forces. Somewhere within that environment, a planetary system must have existed that gave rise to these microscopic life forms and eventually ejected them into interstellar space. The chemical signatures detected by Webb suggest a biochemistry based on carbon, but not carbon alone. Trace metals appear interwoven with organic compounds in structured ways. Trace metals are elements present in very small amounts, yet they can play critical roles in chemical reactions. On Earth, many biological processes rely on such elements as helpers or catalysts. In this case, the patterns observed do not match what Earth-based organisms can produce on their own, pointing again to a fundamentally different evolutionary path. Some researchers speculate that life on 3I Atlas may be older than the solar system itself, descended from a lineage that split from the chemical ancestors of Earth-based life billions of years ago. Others propose an alternative view. They suggest this could be a relatively young life form, one that evolved under conditions so different from those on Earth that it represents a parallel experiment conducted by nature on a galactic scale. Both possibilities carry profound consequences for how life is understood. Taken together, these findings reshape the discussion around life in the universe. They do not provide final answers, but they redefine the questions. If life can form, survive, and remain active within small interstellar bodies, then the spread of life across the galaxy may be far more common than once believed. The implications for panspermia are more profound than ever. For centuries, the idea that life could travel between stars has been treated as a bold hypothesis, often placed at the edge of mainstream science because it seemed to clash with a more familiar picture of biology. Most models of life begin with a stable world, a planet with a steady source of energy, liquid environments that can support chemistry, and long stretches of time where conditions do not swing wildly. In that framework, life is rooted. It begins in one place, adapts to that place, and remains tied to it. The theory that life could move from system to system has never been rejected because it is impossible, but because direct evidence has been missing. If 3I Atlas is confirmed to be a living object, that gap changes immediately. It would not just suggest that life exists beyond Earth. It would directly demonstrate that life can survive the journey through interstellar space itself. That shift matters because interstellar travel is not simply long-distance travel. It is exposure to extreme cold for vast periods of time, constant radiation, and a near absence of stable energy. In ordinary biology, even very tough organisms depend on regular opportunities to repair damage and restore basic chemical balance. A living system crossing the space between stars would need a way to endure long dormancy, resist radiation damage, and maintain at least minimal internal order. If 3I Atlas carries such life, then life in the universe is no longer a fixed phenomenon tied only to the world where it began. It becomes mobile. It becomes something that can spread through natural processes, carried by icy bodies that are expelled from their parent star systems and then drift through space for millions or even billions of years before encountering a new planetary system. There are known physical pathways for this kind of movement. Young star systems are dynamic places. Planets shift position over time. Large bodies exchange gravitational energy. Orbits can become unstable. Small objects, including comets and ice-rich fragments, can be thrown outward by gravitational fluctuations and resonances until they escape the gravity of their original star. Once ejected, they become interstellar travelers, moving silently through deep space. Most of them would be chemically inert archives, preserving whatever formed inside them. A smaller fraction might also preserve something else. If 3I Atlas is living, then one of the most important assumptions in astrobiology has to be updated. Life may not be confined to the places where it forms. It may be capable of being transported, surviving transit, and arriving somewhere new with its internal complexity still intact. This perspective changes humanity's position in the cosmic picture in a very specific way. It blurs the boundaries between biospheres. A biosphere is usually understood as a closed system, like a planet's surface and oceans, containing its own lineage of life. If life can travel freely enough, then biospheres are not fully isolated. They can exchange material. They can share organic chemistry. They might even share living organisms. In that case, Earth may not be an isolated oasis. It may be one node in an ancient network of biological exchange spanning the Milky Way, connected not by intention or design, but by the physics of ejection, drift, and capture. From that idea, a more provocative hypothesis follows. Earth's genetic heritage may not have originated entirely on Earth. It may include a blend of native evolutionary streams and extraterrestrial seeds that arrived long ago and became part of the living system we now see. This does not mean Earth life must have come from space. It means the possibility becomes harder to dismiss when a living interstellar object is present in the solar system. It introduces a mechanism that does not depend on imagination. It depends on drift, time, and survival. If small bodies can carry life across the galaxy, then Earth could have received organic building blocks or even simple organisms during its early history. Those additions could have altered the course of life's development, mixing with local chemistry and shaping what came after. There is another possibility that leads to a different kind of scientific shock. If the microbes associated with 3I Atlas are completely unrelated to life on Earth, then the discovery still represents a major shift in thinking. It would suggest that life is not a rare phenomenon that happened once in an isolated corner of the galaxy. It would suggest that life may have emerged multiple times, under different conditions, using adaptive strategies and molecular architectures that do not match the biological paradigm known to humanity. In this scenario, life is not only mobile, it is also diverse at the deepest level. It would mean the rules we infer from Earth biology may describe one solution among many, not a universal template. Either way, both scenarios expand the astrobiological landscape beyond anything previously imagined. In the first, the galaxy becomes a connected system of biological exchange, where life can move and mix over long time scales. In the second, the galaxy becomes a place where life appears repeatedly, independently, shaped by local chemistry and environment, in ways that lead to different outcomes. Both outcomes require scientists to rethink what common and rare mean in the context of biology. They also force a reconsideration of what kinds of environments should be studied. It would no longer be enough to look only for Earth-like planets in narrow temperature ranges. It would become necessary to take seriously the possibility that life can persist in conditions once thought far outside any habitable boundary. The discovery also highlights the extraordinary resilience of life, assuming the interpretation holds. Interstellar space is close to an impenetrable environment for most organisms. Temperatures are extremely low. Radiation is intense and persistent. There is no stable atmosphere, no liquid environment, and no reliable source of energy. Even if a system could enter a dormant state, it would still face continuous damage at the molecular level. Radiation can break chemical bonds, fragment complex molecules, and disrupt the structures needed for life to function. To survive such a journey while maintaining minimal metabolic reactions, organisms would need protective mechanisms far beyond anything previously confirmed in Earth biology. Webb's data point toward concentrated, radiation-absorbing molecules that could serve as protective pigments or photoprotectors. Pigments, in this context, are not about color in any ordinary sense. They are molecules that interact with light and radiation, either absorbing it safely or converting it into a form that causes less damage. In a high radiation environment, such molecules can act as shields. They can reduce the harm caused by energetic particles and radiation waves. The presence of such compounds would fit an adaptive strategy aimed at survival over long durations in space. Certain spectral features also suggest the presence of polymers capable of repairing molecular damage. A polymer is a long chain-like molecule built from repeating units. In living systems, polymers can be structural, like protective layers, or functional, like molecules that store information and support repair. The idea here is not that Webb has directly imaged repair in action, but that the types of polymers implied by the spectrum could support stability and self-maintenance. Over long periods, even small repair advantages could determine whether a biological system survives or fails. If these polymers act as a form of biological armor, then they represent a level of long-term protection that Earth-based models have not had to produce at such extremes. When compared to Earth's extremophiles, the endurance implied by 3I Atlas appears to exceed anything previously documented. Extremophiles are organisms that live in conditions that would kill most life, such as intense heat, strong acidity, high salinity, or deep radiation exposure. They are often used as examples of life's flexibility, but even extremophiles on Earth still exist within a planet's protective context. They benefit from some shielding, some stability, and cycles of energy availability. The conditions of interstellar space remove those supports. If life can persist there, it suggests evolutionary pressure that does more than favor endurance. It favors stable function under isolation, where failure cannot be corrected by migration, reproduction bursts, or environmental recovery. This is why attention is now focused on what will happen as 3I Atlas moves closer to the Sun. Researchers are careful about discussing long-term consequences or possible public reactions, not because those questions do not matter, but because they are far beyond what can be responsibly addressed while core facts are still being tested. The object's changing environment, however, presents an unprecedented scientific opportunity. Increasing temperatures will alter the structure and behavior of organic molecules trapped in ice. Some compounds may become more mobile, others may break apart or combine into new forms. Increased radiation could trigger chemical cycles that remain inactive in deep space, revealing new spectral signatures that Webb can analyze with high precision. Another change may be even more important. As volatile compounds sublimate, meaning they transition from solid ice directly into gas, they can release trapped material into the space around the object. In comets, sublimation produces a surrounding cloud of gas and dust. If 3I Atlas contains microorganisms embedded in its ice, sublimation could release them into the near environment. That would not create an atmosphere in the planetary sense, but it could create a temporary, localized envelope of material. Such a cloud would provide observers a better chance to detect more detailed samples because molecules and particles in the cloud can produce clearer spectral signals than material locked under layers of ice. For now, the scientific community's focus remains on a single point: the Webb telescope's landmark discovery, the increasingly compelling evidence for extraterrestrial life, and the consequences that follow for biology, astrophysics, and humanity's understanding of the universe. Early interpretations of the discovery already acknowledge the overwhelming complexity of what it could mean. If life exists on 3I Atlas, then many assumptions about the origin of life on Earth must be re-examined. Scientists remain cautious. They are not prepared to conclude that Earth life definitely came from outside the solar system, but the presence of life forms on an interstellar object supports the argument that organic building blocks, or even intact organisms, may have played a role in seeding early Earth. The idea of life being transported across the cosmos has always been intriguing, but it has also been highly speculative. It has often lacked a clear, testable pathway. With an icy messenger like 3I Atlas passing through the solar system, that pathway becomes more plausible. It becomes anchored in a real object, with real signals that can be measured and retested. Still, the scientific effort is not centered on far-reaching speculation. It is centered on the discovery itself and the careful work of confirming what the data actually show. One of the most important outcomes of this discovery is that it highlights the dynamic interconnectedness of the galaxy. If 3I Atlas harbors life, it suggests that the Milky Way is not simply a loose collection of isolated star systems. It may function as a vast exchange network where matter and energy move constantly, and where life might also move under the right conditions. As young star systems form, as planets migrate, and as orbital paths are disturbed by gravitational resonances, many small bodies are ejected from their familiar environments and sent into interstellar space. Some of these bodies may carry organic matter, a smaller number may carry early life. In either case, they take their origins with them, traveling across the galaxy for millions or billions of years. Over those long spans of time, interstellar travelers become invisible carriers of information from distant systems. They preserve chemical and possibly biological traces of the environments that formed them. In most cases, they pass unnoticed, never approaching a world where they can be studied. Webb's findings suggest the Milky Way may be filled with such travelers, each one a hidden archive of its biological environment, waiting for a civilization advanced enough to recognize and decipher it. The complexity that Webb has revealed on 3I Atlas leads to a conclusion that would have seemed far too daring only a short time ago. Life may not require a stable planet in order to form or persist. For decades, planets and large moons have been treated as the most promising environments for biology because they offer steady energy sources, long-lasting chemical stability, and protective layers such as atmospheres or magnetic fields. Those assumptions were reasonable, based on the single example of life that humanity knows well. Yet the data emerging from 3I Atlas suggests that stability at a planetary scale may be helpful, but not strictly necessary. Under certain conditions, much smaller bodies may also be capable of sustaining life for extremely long periods of time, even when they are far from any star. Interstellar objects like 3I Atlas are not solid blocks of uniform ice or rock. Their interiors are complex. Over long spans of time, repeated heating and cooling, radiation exposure, and internal stresses can create hollow cavities, porous networks, and microscopic channels. These internal spaces may act as sheltered microbiological environments. Within such cavities, temperatures can remain above absolute minimum levels. Radiation can be partially blocked by surrounding material, and chemical gradients can form naturally. A chemical gradient is a difference in concentration or energy that reactions can draw from, and even simple gradients can support basic biological processes. If organisms inside these cavities are capable of prolonged hibernation, the picture becomes even more compelling. Hibernation, in this context, does not mean sleep as humans experience it. It means a deep reduction of activity to near zero, where chemical reactions slow dramatically and damage accumulates very slowly. If such organisms awaken only when external conditions change, such as during a close approach to a star, then the cold isolation of interstellar space may not fully extinguish life. Instead, it may place it into a waiting state, preserving it across immense spans of time. Seen this way, 3I Atlas is not simply a visitor passing through the solar system. It becomes a fragment of a much larger and still incomplete galactic puzzle. For centuries, humanity has asked whether it is alone in the universe. That question has often been framed around distant planets and distant stars. 3I Atlas introduces a different possibility. The answer may arrive not from a faraway world, but from a small body drifting quietly between stars, carrying evidence that life can exist in forms and places once dismissed as impossible. Much of the current discussion has focused on the nature of the chemical systems that Webb has detected. The organisms inferred from the data, if they can be described as organisms, appear to rely on a biochemical toolkit that blends familiar elements with unfamiliar strategies. Carbon remains central, as it does in Earth life, but it is not acting alone. Heavy metals appear to be incorporated into the molecular framework in meaningful ways. Heavy metals, present in very small amounts, can serve as powerful catalysts, enabling chemical reactions that would otherwise proceed too slowly or not at all. On Earth, most biology relies on organic enzymes. These are complex molecules that speed up reactions, but are also relatively fragile. They can be damaged by radiation and extreme conditions. The data from 3I Atlas suggest a different approach. Some researchers have compared the inferred structures to metallic microstructures or nanoscale frameworks. Instead of depending entirely on delicate organic components, these systems may use hybrid biochemical machinery that combines organic molecules with mineral-like elements. Such a combination would be far more resistant to radiation and temperature extremes, offering a practical advantage in the chaotic environment of interstellar space. As more observations accumulate, the picture of 3I Atlas continues to grow in detail. It is not a homogeneous object with uniform composition throughout. Its structure appears layered and varied. There are dense regions of ice, extensive porous networks, rocky inclusions embedded within frozen material, and pockets rich in organic compounds. These organic rich pockets are especially important. Spectral signals indicate that they host the highest concentrations of biologically relevant molecules, suggesting that they may be the primary zones of activity. These pockets do not all behave in the same way. Each appears to maintain a slightly different chemical balance, shaped by its local environment within the object. Some receive more heat during rotation, others remain shielded for longer periods. This variation creates what can best be described as miniature ecosystems. Each pocket operates under its own conditions while still being part of a larger connected system. Such internal diversity is difficult to reconcile with the idea of a static chemical relic left over from ancient processes. Webb's instruments have tracked fluctuations within these regions over time. The changes follow cycles that rise and fall in connection with the object's rotation, its exposure to sunlight, and the uneven distribution of internal heat. These cycles repeat. They show patterns rather than random drift. In chemistry, repetition and regulation are meaningful. They suggest that processes are being maintained, adjusted, and rebalanced rather than simply decaying. This reinforces the interpretation that 3I Atlas hosts a living, adaptable system rather than frozen remnants of long-dead reactions. One of the most significant consequences of this discovery is how it reshapes our understanding of the chemistry of the interstellar medium. For many years, astronomers have studied the space between stars and found it rich in complex molecules. Water, carbon monoxide, methane, and polycyclic aromatic hydrocarbons have all been detected in molecular clouds. These findings were surprising on their own, but the leap from molecular complexity to true biology always seemed too large. Chemistry, it was thought, could travel far, but life could not. 3I Atlas now appears to bridge that gap. It stands between interstellar chemistry and living systems, showing how one might lead to the other. If life can persist inside small bodies moving through interstellar space, then molecular clouds are not just chemical reservoirs. They may also act as staging grounds. They provide raw materials, and they may receive life-bearing debris ejected from planetary systems. Organisms embedded in such debris could drift through star-forming regions like seeds carried by a cosmic current, moving from one environment to another over time. This perspective makes the idea of life as a galactic phenomenon increasingly plausible. Instead of viewing biology as a rare feature tied to a few special planets, it becomes possible to see it as an outcome that arises naturally from galactic chemistry under the right conditions. Webb's discovery has prompted scientists to reconsider the assumed rarity of life. If life can exist on an object as small as 3I Atlas, enduring the harshness of interstellar space, then the emergence of life may not be a cosmic accident. It may be a recurring result of processes that operate throughout the Milky Way. Some researchers have gone further, suggesting that the life detected on 3I Atlas could represent only a tiny fraction of a much larger, invisible biological presence spread across the galaxy. This idea remains speculative, but it follows logically from the data. If one such object exists and can be detected, there may be many others that pass unnoticed, either because they remain distant or because their signals are too weak to stand out against background noise. Despite the scale of these implications, scientists remain firmly grounded in evidence. The focus has not shifted towards speculation about future encounters or philosophical consequences. Attention remains on what can be measured and confirmed. Researchers concentrate on spectral data, looking for repeating molecular signatures and rhythmic shifts in concentration. They map where potential biomarkers are strongest, tracking how these regions change across the surface and interior of the object. Each new dataset sent back by Webb adds clarity and confidence without pushing conclusions beyond what the evidence supports. The guiding principle throughout this work has been restraint. Extraordinary claims require extraordinary evidence, and the scientific community is well aware of that standard. What makes 3I Atlas so compelling is not a single dramatic signal, but the convergence of many independent observations. Together, they point toward a conclusion that was once considered unthinkable. This interstellar body does not behave like an inanimate object, shaped only by physics and chemistry. It behaves like a vessel, one that carries microorganisms across the interstellar boundary. 3I Atlas's approach does not create urgency. It creates anticipation, because the closer it moves toward the sun, the clearer the biosignatures appear to become in the data. More sunlight means more energy reaching the surface and the near-surface layers, and that energy changes how trapped materials behave. Organic compounds that were quiet and locked in ice begin to react. Volatile materials begin to sublimate, shifting directly from solid to gas and building a thin haze around the object. That haze matters because it carries organic material out into space where it becomes easier to measure. When the material is trapped under ice, signals can be muted or blended together. In a surrounding cloud, the same molecules can leave cleaner spectral marks. This is why, as the haze thickened, Webb was able to collect more detailed spectra and identify compounds that had been hidden before, not because they did not exist, but because they were sealed away and difficult to separate from the background. What began as a faint light pattern quickly developed into a more complex halo of activity, and the halo was not uniform. The molecular patterns inside it suggested organization. Researchers saw clustering, where certain molecules appeared together in repeated groupings instead of being spread evenly. Some compounds appeared to form protective structures around a central chemical core, while others extended outward in patterns that looked more like a scaffold than a random cloud. A scaffold, in simple terms, is a supporting framework. Here it describes molecules that seem to create shape and spacing, as if they help other components stay in place or interact in a controlled way. These signs pointed toward internal cooperative systems, not necessarily complex life as humans imagine it, but coordinated chemistry that behaves more like a community than like isolated particles. In the interstellar medium, where radiation is constant and energy is scarce, cooperation can be a survival strategy. If one component can shield another, or if multiple components can share captured energy, the system as a whole becomes harder to destroy. The patterns in the haze were consistent with that kind of shared protection and shared function. Each new observation added weight to the same core point. If these signals truly reflect biology, then biology is not limited to planets. It can travel, persist, and express itself in places that do not offer stable warmth, a thick atmosphere, or a reliable day and night cycle. That idea changes the role of the James Webb Space Telescope in a way no one planned for at the start of its mission. Webb was designed to study distant galaxies and faint infrared light, to map early cosmic history, and to measure the chemistry of faraway worlds. Yet its sensitivity and resolution also make it capable of detecting subtle variations in complex carbon compounds close to home. even when those variations are faint, layered, and changing over time. In the case of 3I Atlas, Webb's instruments did more than list molecules. They revealed relationships between molecules. The data began to look less like a simple inventory and more like a map, showing which compounds rise and fall together, which appear linked to radiation changes, and which only appear when the haze reaches certain densities. That kind of pattern tracking pushes the study of life beyond a purely planetary framework. It turns part of the question into one of biology at galactic scale, where the unit of study is not just a planet's surface, but a traveling microenvironment that can remain active across interstellar distances. As the observations continued, more researchers converged on a cautious consensus that biology may not be an exclusive feature of Earth. The implications of 3I Atlas touched every discipline that studies life, energy flow, adaptation, and the long-term evolution of complex systems. Scientists avoided public speculation about the long-term consequences, not because the consequences are unimportant, but because the evidence still needed to be treated with discipline. Still, within the work itself, there was recognition that the moment was historically significant. The data suggested the universe is not chemically quiet in the way older assumptions implied. Life, if present here, is not a distant rumor. It is a dynamic process that can drift among the stars and still respond when conditions change. This is not framed as a conclusion about intention or purpose. It is framed as a measurable phenomenon unfolding as a fragment from a distant system moves through the solar system under continuous monitoring, with sensitivity no prior telescope could provide. As the brightness around 3I Atlas increased, it became a record of internal change. The spectral signatures did not stay fixed. They shifted as the object moved into warmer regions and as sunlight drove new activity. Each shift revealed another layer of information about what might be happening inside. Researchers observed that what looked like initial organic changes did not remain isolated events. They developed into chains of reactions, where one molecular change was followed by another, and then another, like a set of ripples spreading through a connected system. These were biochemical ripples in the sense that they involved compounds commonly associated with biological structure and energy handling, even if the exact pathways did not match anything known on Earth. The changes occurred quietly, without explosions or visible drama, but their scientific value was high because they offered time-resolved clues. When scientists can track how signals evolve, they gain a way to test whether a system is passive or responsive. A passive system tends to follow simple heating curves and predictable decay. A responsive system can show regulation, timing, and selective activation. To decode these patterns, researchers broadened their analysis beyond the large and obvious molecules and began focusing on smaller compounds that had been easy to overlook. Small molecules can matter because they often serve as intermediates. An intermediate is a step in a chain, a chemical that appears briefly as one process turns into another. Several of the newly tracked chemicals matched the role of intermediates in energy metabolism and in building structural components. Metabolism, in basic terms, is how a system manages energy and materials to keep itself going. Even a simple organism must capture energy, store it, use it, and protect itself from damage. The data showed that concentrations of these intermediates fluctuated over time. When plotted as activity curves, those changes were reminiscent of metabolic rhythms on Earth. where chemicals rise and fall as a system turns pathways on and off. At the same time, the details did not align with any familiar biochemical system. The timing and combinations were different. The dependencies on radiation and temperature shifts were different. That mismatch is important. It suggests this is not Earth biology reproduced elsewhere. If it is biology at all, it may be a separate solution, built from the same broad ingredients, but assembled under different rules. The reaction patterns also appeared to form a branching network rather than a single line. In a branching network, one pathway can split into several options, and the system can shift which route dominates depending on conditions. That kind of flexibility is common in living systems because environments change, food sources change, energy availability changes, damage accumulates. A branching network lets a system respond without collapsing. In the interpretation being tested here, each node of the network represents a function the organism can activate when conditions favor it, such as increased light, increased surface activity, or changes in the surrounding haze. This is not presented as proof of intention. It is presented as consistent with regulation, which is one of the key differences between lifelike behavior and uncontrolled chemistry. One detail that stood out across repeated analyses was what these reactions did not seem to rely on. Many of the pathways appeared to depend less on liquid water and more on supercooled volatiles that can remain stable at extremely low temperatures. Volatiles are materials that can change phase easily, like certain ices that sublimate when warmed. When supercooled, they can still support slow chemistry in protected pockets, creating a stable microenvironment even in deep cold. That matters because it offers a way for reactions to proceed without requiring an Earth-like ocean or an Earth-like atmosphere. In protected cavities, a thin film of supercooled volatiles could provide enough mobility for molecules to meet, react, and reorganize, while surrounding ice and rock provide shielding. Taken together, these clues point toward a form of biology that operates according to unfamiliar but consistent rules. The rules are unfamiliar because they are not built around liquid water at moderate temperatures. They are consistent because the data show repeating patterns, timed responses, and structured relationships that do not look like random chemistry. Another element caught the researchers' attention as the signal quality improved. Hidden within the organic-rich pockets, Webb's infrared data suggested the presence of small crystalline structures. These crystals did not appear to be part of the original bedrock of the object. Instead, they seemed to have formed over time through repeated cycles of sedimentation and dissolution. Sedimentation is the settling and layering of material. Dissolution is the breaking down and remixing of material into its surroundings. In a small body with pockets, pores, and temperature gradients, these cycles can occur in miniature. A region warms slightly. Materials move or dissolve. Then it cools, and they refreeze or settle in layers. The crystals carried thin layers of organic compounds arranged in a layered sequence, like a physical record of past cycles. Some layers suggested gradual accretion, built up slowly over time, while others looked like they formed more rapidly, likely in response to sharper changes in temperature or radiation. This kind of layered structure is useful scientifically because it can preserve a timeline. It can store evidence of repeated environmental shifts and how the chemistry responded, one layer at a time, without requiring a direct view of the interior processes while they happened. With each new spectrum, the objects surrounding haze and its internal pockets continued to reveal patterns that were more detailed and more structured than the early signals suggested. None of this removes the need for caution, and none of it replaces the need for continued verification. But the direction of the evidence remained consistent. As 3I Atlas nears the Sun, the system becomes easier to read, and the signatures become harder to explain as inert coincidence. The work now is to keep measuring, keep comparing, and keep narrowing the explanations to what the data can actually support, while the object itself continues its quiet passage through warmer light, and the record it carries continues to unfold layer by layer in the infrared. And then, as the haze drifts outward and the spectra settle into the next set of curves, the analysis continues in the same calm way, with the sense that something very old is being observed in real time, not loudly, but steadily, as the signals fade into the background and the next observation window begins.